Okay, so good morning, everyone. I am Anuj and my teammate Preeti. Today, we are here to present our understanding and takeaways from the paper RL Square Fast Reinforcement Learning via Slow Reinforcement Learning. So, just sit back and enjoy your cup of coffee, and let's get started. Before we jump right into understanding of the paper, let's first understand what reinforcement learning means. So as discussed in class briefly, reinforcement learning is an algorithm that collects data interactively. It enables an agent to learn in an interactive environment by trial and error using feedback from its own actions and experiences. In this way, deep reinforcement learning has over the years proven to be successful in learning complex behaviors. Although one of the greatest disadvantage is the expense of high complexity and huge number of trials required to train the algorithm. In this paper, to support this argument, author gives an example of Atari Games, a popular arcade games platform where applying reinforcement learning takes tens of thousands of episodes of experience per game. It takes about days to master the game. Animals, on the other hand, learns faster from less trials and prior experiences of the world. This paper mainly focuses on bridging this gap. So, to further discuss about the idea and formulation about the algorithm presented in the paper, Preeti will take over.
So the idea of the paper, like Anuj mentioned from his closing notes, that how animals and humans tend to use the prior experience to decide or even learn a particular task. So the authors took inspiration from this way of learning. And initially, they had discussions to use Bayesian reinforcement algorithm. Now, what is Bayesian reinforcement algorithm? So the main idea of Bayesian reinforcement algorithm, which kind of sets it apart from other algorithms, is the fact that it can maintain the distribution over various quantities like the model parameters, the value function, and the policy or even the gradients. So since it can take care of the prior states, that was one reason they were looking into Bayesian reinforcement learning. And the other advantages also include how Bayesian reinforcement learning reduces the complexity of solving a problem. In addition to that, it also takes less amount of time in training, or it takes less number of episodes to train a particular task, and it also reduces the amount of time it takes from number of weeks to just a few number of days. But a major disadvantage was that the assumptions that it makes about the environments. So because of the assumption it makes about the environments, the methods cannot be interactable when it's working on a high dimensional setup. So because of the disadvantage, the authors decided to use a new approach that is defined in the paper. So instead of designing an RL algorithm, the paper suggests learning an algorithm from scratch. So what happens here is the author has proposed a hand-assigned way for a specific RL algorithm. So here there are four important things to note. The first thing is the main objective. The main objective of the paper here is nothing but the learning process of the agent itself. And the main thing that they have to do is to make sure that this main objective is averaged among all the MDPs. MDPs are nothing but the Markov decision process. And the next thing is the agent is structured to be a recurrent neural network. So it basically holds all the previous observations, including all the rewards, the actions, and any flags that it has. And the last thing is the learned agent is also expected to adapt to any new task given to it when it's deployed. So this is the idea of the paper. Now coming to the formulation. So in formulation, the main objective is to maximize the reward across the trials rather than each episode. By this is the formulation that was proposed in the paper. As you can see, here they have shown two trials. So each trial is specific to an MDP, and inside each MDP we have two episodes. That is what is defined. So for each MDP, they have defined it to have two episodes. And let's look at how these MDPs actually work in detail in the next slide. So coming to the formulation again. Now, what the authors have done is, first, for an MDP, we have an initial state, which is S0. And basically, the MDPs are nothing but these MDPs are chosen from a bunch of probability distribution, and this is a subset of this probability distribution is what is used to train the model. So initially, you have a initial state called S0, and this initial state, when passed to our hidden state, we get an action that can be performed. And for that action, when performed, we get a certain reward. And this action and reward together generates the next state, which is S1. So this state S1, along with our rewards and actions, together helps us compute the next hidden state, which is H1, along with the previous hidden state, which is H0. So this process continues until this a particular episode ends. So now, as you can see, we have our state S2, from which we get our hidden state H2, and then so on until this particular episode ends. So this is the end of episode 1. After episode 1, there's an interesting fact here. By the end of each episode, the hidden state is preserved to the next episode. That is, once an episode is done, we again start with a new state, which is S0, initial state, but the hidden state that we're using will carry forward from the previous hidden state. So instead of having a H1 over here, we'll have a H4, which is our fourth hidden state. So this goes on until we finish this particular episode. So now, as you can see, inside this particular MDP, we have about 2 episodes as defined in the problem. So these MDPs, this is a sample MDP, and there are going to be multiple MDPs as such until the model is trained. So now coming to the policy. So the policy that is discussed in the paper by the authors are, first, the policy that is used here is RNN by itself. And one key thing to note here is the RNN can face this problem of vanishing or exploding variants. And to tackle this particular problem, the authors suggest the use of a GRD, which is a gated recurrent unit. And this is the representation. When coming to the optimization, the authors have chosen an off-the-shelf optimizer, which is TRP, and along with generalized advanced estimation. That is because to make sure the variance is handled well, and the balance between the bias variance trade-off is taken care of. So this is the policy. And now coming to the experimental setup, I'll give it up to Anuj to talk more about it.
So as we have understood the formulation and implementation of the policy, so let's further discuss about the experimental setup. The authors of the paper have evaluated based on 2 questions. First, if RL square performs well on MDP classes when compared to other existing algorithms. And the other question is whether this algorithm can be scaled up to high dimensions or more complex tasks. To answer the first question, an evaluation is done on 2 sets of tasks with known MDPs. First is multi-armed bandits and second is tabular MDPs. These problems are chosen especially because they are studied extensively in reinforcement learning algorithms. And in order to answer the second question, RL square is evaluated on more complex tasks, especially a vision-based navigation task to check if it performs well on high dimensional tasks. So we'll start to know about multi-armed bandits. So to start with, author decided to evaluate the performance on multi-armed bandit, that is MAB. MAB problems are subset of MDPs where the agent's environment is stateless. As the name suggests, it has multiple arms, and the question is what arm to pull in order to receive the maximum reward. One of the best example of MAB is to imagine a gambler at a row of slot machines who must decide which machine to play, how many times to play each machine, and in which order to play them in order to gain the maximum reward. Especially in this experimental setup, there are K arms, and at a given time, one arm is pulled, and it receives a reward from Bernoulli's distribution. And the key challenge is to find a balance between exploring all the available arms and switching over to the best arm to exploit more. Using the RL square algorithm, author trained an RNN policy to solve the MAB problem. It can be observed in the table that RL square achieves almost as good performance to other MAB strategies like random, Gettin's index, Thompson sampling, upper confidence bound. In the above table, N represents the number of episodes and K is the number of bandits. It can be observed from the table that RL square outperforms them in finite horizon settings. It is mainly because they minimize the asymptotic regret rather than finite horizon regret. Although in one of the scenario, it can be observed where episodes are 500 and there are 50 arms, Gittin proves to outperform RL square, suggesting some room for improvement when using other algorithms from RL square. So, Preeti, next slide. Yeah. Learning curves for various settings are shown in the figures, and it can be observed from the figures that RL square achieves best scores in less number of iterations. And as seen on the previous slide, Gittin's algorithm performs well compared to other algorithms, and therefore the performance of the curves is normalized such that Gittin's scores 1 and random policy scores 0. It can also be observed in figure C that Gittin's outperforms RL square, which raises the question if better architecture or better RL algorithms should be explored. So now Preeti will take over.
To talk about the next experimental setup, which is a tabular MDP. What is a tabular MDP? So tabular MDP is also a subset of MDPs, but just that we'll be dealing with a finite number of states and actions. Now, why do we use this experimental setup? So now, as Anuj was talking about the multi-arm bandit problem, we understand that it gives us a very natural and proper understanding of how to learn to trade off between the exploration and exploitation. But the problem does not involve any decision making as such, and it does not fully characterize the challenges of solving an MDP. So, because of this, an experiment was performed on tabular MDPs as well. So, whatever algorithms that were used in the MAB problem, we're using the same methods here, but just we have two other new additions, which is our PSRLU, which is posterior sampling for reinforcement learning, and also BAB. So now, from these methods, this is what was observed. Again, RL square does outperform most of the other strategies, but when the value of n is less than 50. But once the value of n is greater than 50, we see that RL square does not perform as good. So this is also better represented in the graph over here. So what the authors are trying to say from this is that the RL square do outperforms when the n value is less than 50. But this also signifies that when the n value is less than 50, it gives the algorithm more chance to exploit and explore more. And in case of n when it increases, the RL problem becomes very hard to solve the outer loop. So that's the reason it doesn't perform well for n greater than 50. And now coming to the visual navigation, which is the third setup. Like Anuj mentioned earlier, here we're trying to understand how RL square will perform in a high dimensional environment. So for this setup, the authors have created a very small visual navigation setup wherein they have an agent and you have a target, and this agent is supposed to randomly navigate through the generated targets and reach this particular, generated mazes to reach the particular target. So this was what was proposed. As you can see, there are two figures here. One is a 5x5 maze and a 9x9 maze. So we know that visual navigation is a challenging task by itself. So to understand the use of memory, the author suggested two ways to do it. One is using a 5x5 maze, other is using a 9x9 maze. So the observation from this was when training it in a 5x5 maze, it was noticed that the agents were able to learn through the paths easily and preserve whatever they've learned from the previous stages and also reach the target. But in case of 9x9, although the agents were able to preserve the paths and the learnings from the previous state, since the surface area, the trajectory here is a lot bigger than the 5x5 maze, it was not able to optimally choose which paths to take. So it appeared to be more confused in 9x9 maze. So that was the conclusion over here. So now going to our conclusion from the paper, I think Anuj will take care of this.
Yeah. So after studying about the policy implementations and three different experimental setups, let's summarize the paper, like what we learned a few things from this paper. The paper suggests using different approaches for better designing the reinforcement learning algorithms. So instead of focusing on the particular task, the aim is to learn the algorithm instead from end to end. The second thing is that on small scale task, the proposed RL square gives comparable performance to the theoretically justified algorithms. And the algorithm can also be scaled up to high dimensions or more complex tasks. It is observed that the performance degrades as the horizon gets longer or if the individual task becomes more challenging. So taking the learnings from the paper, we thought that this paper can be used to explore more in the fields, like instead of using a trust region policy optimization to learn, any other different model can be used. This algorithm RL square can also be used to implement on real world problems, and it can be scaled up to use in different environments. In the end, we are also trying to implement the paper and will share the results in our report. Yeah, thank you.
Thank you.
Yeah.
Do you have